It's my pleasure to introduce Lavi Lazarovitz. I kind of got there nearly, yeah. Lavi is the Group Research Manager at CyberArk. He leads a group of security researchers in vulnerability research and writing about information security, which you may have seen in some magazines and blogs around the world. Lavi is also into researching and coding prototypes and proofs of concepts. Working alongside a dedicated team, he studies the methods and tactics employed by hackers to penetrate and move laterally across an organization's network. He's responsible for devising effective detection and mitigation techniques to thwart cyber attacks. If you could please welcome Lavi to the stage.
Thank you. All right, so first of all, good morning, and I would like to start by complimenting you by making a great choice this morning to see this talk. I'm sure it will be different. Usually, this kind of sessions tend to be a little bit best practices, a little bit strategy. I'll try to deep dive into the details without making it boring as hell. I'll try to do that. So allow me to start. A few years ago, many digital businesses got a new shiny block. About 11 years ago, if we talk about Linux containers, and about 6 years ago, if we talk about Docker. Now, if you are securing containers in the organizations you are coming from, or if you're dealing with containers, then I have a couple of insights to share with you today that are usually not talked about a lot. So this is the plan, and I also should say that this session is based upon research that we at CyberArk Labs worked on, and I'm really proud to be part of that group. My name is Lavi Lazarovitz, and I'm really proud to lead one of CyberArk Labs groups that focus on the security of emerging technologies. Emerging technologies like cloud platforms, like automation tools, DevOps tools, and so on. So our recent research focused on the security of Azure, AWS, and also Jenkins, Kubernetes, and of course containers. Now, I should say that this session is based upon a research that is full of ton of details related to Linux kernel and syscalls and kernel stuff. Very ugly C code. So it was a tough challenge making this session interesting or bearable, especially if you consider that what you see here on the bottom of the screen is the climax of the research in this session. So this is how it looks like, and I'll return to that later, and I'll explain a bit about that. So to make things a little bit more interesting or bearable, if you may, I chose to tell the story of the Great Houdini. The Great Houdini was famous for escaping handcuffs and straitjackets and, of course, containers. So a perfect fit for the story. And so this session called, you see here, The Great Escape, is actually about challenging Houdini to escape a new type of container using new trick. So this is what this session will be about. And just to get in the mood, I have a little video for you showing Houdini doing his sensational escape. Let's have a look. now we're in the right mood. So there's another reason I show you this little clip, and the reason is that the straitjacket that Houdini wore was limiting his ability to move his hands, and the fact that he was hung in mid-air isolated in somewhat controlled environment. Same works, of course, for containers that limit a process ability to interact with the host system, to interact with the file system, to interact with the network stack, the IP tables, the firewall rules, other processes. This is how it works. And to show you how process isolation looks like in a raw Linux command, this is how it looks like. What you see here is the essence of process isolation we call today container. And the unshare command or syscall that you see here, disassociated part of the process execution context. Now, let me explain this. What does it mean? So the raw Linux command that you see here forks a new bash process, create a new bash process, a new command line, and then start building a walls around it, which will be our container. So it separates our process, our new process, with a new process ID namespace, with a process namespace. So our process, our new bash process, won't be able to see other processes. It builds a network isolation or network namespace, meaning that our new process won't be able to rely on the host, IP tables, routing configurations, and so on. Inter-process communication namespace, meaning that our process, our new bash process, won't be able to communicate or pipe into other processes. UTS namespace, Unix time sharing, which allows us to name our new environment, and hanging our process in mid-air, which is isolating it from the rest of the file system. This command that you see here is how containers are born. These walls that you see here are the very same walls that are used by both open source and commercial containers to isolate it and secure it in a controlled environment. This is how it looks like. Now, I should also say that the container, the pretty basic container that we built here, is absolutely useless. You can't do nothing with it. It's completely isolated. So it's not really fair with Houdini to ask him to escape this, and it's not really usable. So to make things a little bit more functional and usable, I have this list of commands here. I'll explain in a moment. To allow our new bash process some basic functionality, and to allow our Houdini or attacker to breathe within that container, we need to poke a few little holes in our new isolated process to allow us to use it. And what you see here on the screen is actually two shells. One on the host, a little bit cut in here, and another shell which also starts on the host. So you have two separate shells on the same host. One will end up as a usable container, and the other one will just stay a shell on the host. And this is how it looks like. We start with the unshare command that I mentioned before. Let's see it. There we go. The unshare command, we build the walls. Then we start poking holes. The first hole that we poke in this environment is a hole in the network namespace. What we're actually creating on the container side, we are creating a virtual interface. We are setting it up. And on the host side, we tell the host to attach to this new interface, the new VEth1, virtual interface 1. And we also tell it to forward incoming and outgoing packets. So this is the first hole that we poke in this environment. The other hole that we poke is the around file system isolation. We mount basic directories and files, the tempfs, sysfs, and so on, to allow our new process to have some basic functionality. We also name our new container Houdini's container. We change directory into it, and we root the door behind us, meaning we jail ourselves into a new file structure system. Now, we have a more functional container. We have walls, and we have little holes in it to allow us basic functionality and communications. Now, this is a more fair case with Houdini, and on the other hand, this is a more operational raw Linux container. This is how it looks like. Now that we've seen the walls, the namespaces and walls of containers, we can play with it a bit. And I want to first run a quick, not so sensational escape using a POC called Shocker that was developed back in 2014. This is not CyberArk Labs' work. This is partly why this is not so sensational. But after running Shocker, we'll have read access to any file on the host system, any file. Let me show you how it works, and then we'll discuss what's going on. There we go. Okay. So our starting point is already within the container. Now, just from the attacker perspective, it's not always obvious that we are within the container. So one of the first things that the attacker will do is try to sense the environment. And looking into the file system, there are some indicators, and these indicators are the file system is very, very lean. Not many files, not many processes that are running in the background. This is a pretty significant indicator. Another indicator that we are running within the container, besides the fact that we have the container ID here, which won't always be here, is looking at the C groups. So, I think I have it here. There we go. So looking at the C group, we see that the Linux control groups assigned a specific control group for our container, which means that our container ID here is limited with the resources it will be allowed to use. So this is another significant indicator that within the container. Now let's try to break out of the walls that we just, that the Docker built around us. If we try simple stuff like trying to go to the root file system of the host, will obviously be denied. Okay, this is an obvious, a very naive attempt. Now let's use Shocker and discuss what it does to enumerate a specific file in the file system, which is the etc password, where the usernames and in some cases hashed passwords are stored. So let's have a look, and I'll discuss what's going on. So this is the output of the etc password file system on the host, which I shouldn't have access to. So let me explain how it works. Okay, so when running Shocker, it is targeting the etc shadow file. Okay, this is embedded within the code. Now, what I didn't tell you is that in the container that Houdini is in at the moment, there is a special mount, meaning within the container, Houdini can reach a specific file. This file is resolve.conf, but it could be any file. The ability to access this file allows Houdini to retrieve a structure called a file descriptor, which is the metadata of the file in the file system. Within this structure, there is a special field called inode, which is the bottom line is a number that represents the file in the file system. Now, what Shocker is able to do is take this number, this inode, and just rotate it. Just look for, insert another number in it. And this is what you see here. Shocker just enumerates the number, the inode, and it finds the home directory, the serve directory, the bin directory, and so on, till it finds the etc directory, which is on our path to the target. So after finding the relevant inode, it found the etc directory, and then it started doing the same for the shadow file. And this is what you see here. There is another thing going on here requiring Shocker to do 32-bit brute force. I won't get into it, but it's nothing serious. And as you see here, it happened really quickly. So after enumerating all the inodes for the shadow file, it eventually found the relevant inode. And after getting this inode, what Shocker is able to do is insert this inode within the file structure that it had for the result conf and ask from the system, from the kernel, to read that file. And so this is what you see here. This is the output of the etc password within the host file. So this is how Shocker works. It allows only read access, so it is pretty limited. But you see that we broke out of the firewall, not firewall, but a file system isolation. So this is the first thing that I wanted to show you. Second sensational escape is one that we worked on in CyberArk Labs. This escape is a little bit more complicated. I have a video demo here with me, and I'll show you in a moment. This escape allows Houdini, or the attacker, on the other hand, to compromise the host when certain conditions are met. Let me show you how it works, and then we'll discuss what's going on behind the scene. Okay. So as before, we start already within the container. What you see here is we downloaded a special kernel module. I'll discuss this in a moment, to the container. And we also enumerated the processes running at the moment within the container. Again, those are pretty limited, and it is a pretty significant indicator that we are within a container. And we also see that there is a Docker container D process running, which means there is a Docker within a Docker situation here, which is a very significant indicator of something. I'll discuss it in a moment. All right, so first thing that we do once within the container is enumerating the namespaces. The IDs that you see here are the IDs of the different namespaces assigned to our container. These are the walls that I discussed before. These namespaces will be our target. We try to escape those namespaces. Now, if we try to use the nsenter command, which allows us to change namespaces, enter another namespace. And what we try to do here is change our namespace to the system namespace, the host system namespace. Now, obviously, if we can do that, we can change the context of our process to the system context, meaning we own the host. But obviously, we got an error. Docker prevents us doing so. So we are going to bypass that, and we're going to use here, the NSX that you see here, is actually a special kernel module. Now let me quickly explain. Kernel modules are an extension of Linux kernel. It allows us to load a new functionality to the kernel without rebooting the machine. So for example, if you plug in a new hardware into a Linux server or machine, instead of having to reboot the machine, a Linux kernel might be loaded and allow us to use this new hardware. So this is what we are going to do here. We're going to load a new kernel that will manipulate the nsenter control. This is a great question. I'll answer your question in a moment. Okay, so again, we are enumerating the namespaces. The IDs that we are targeting will soon be changed. We're using ins mode, insert module, to the current kernel module, to the current kernel. No error, so seems successful. Now we are enumerating the namespace IDs again within the container. And we find something interesting. The IDs of the mount and the network namespaces has changed. So this is a good indicator that something good has happened, for Houdini at least. We are still within the container. This is the process, the list of processes that you see here. But now, if we'll try to use nsenter again and change the context to the system context, system namespace, you'll see something funny. The kernel returns with TTY name failed success. So the kernel is a bit confused whether we failed to load the kernel and change the namespace or succeeded in doing that. TTY name is a typewriter which basically means that we just connected our input and output to the system context. This is what TTY stands for. So now, if we'll try to enumerate again what processes are running, we have a completely different picture. And also, if we look at the file system, we'll see that we have the host file system. So we broke out of the file system isolation, we broke out of process isolation. Using this type of attack, we can compromise the host completely, not just having a read access to it. Now, let's demystify the attack and answer your question. So what allows us to, for the shocker, enumerate inodes and read files that we shouldn't have, and what allows us to load a new kernel module? This is something called capability or capabilities. These capabilities are essentially distinct permissions that were broken out of the root user in the Linux root user, meaning that instead of having user or processes in Linux, instead of granting users and processes full root permissions, we can assign them specific capabilities for their task or processes to run. So it is actually a pretty good least privileged implementation. Same applies for containers. Containers also can be assigned specific capabilities. And it is needed in many cases. It is needed when running container within a container. To do that, the containers needs to have certain capabilities to run this virtualization, one inside the other. Also, containers that run file system jobs, that run configuration management jobs also require capabilities. Kubernetes, if you have Kubernetes within your environment, many of the management containers that come default with Kubernetes run as privileged containers with capabilities. So what capabilities were used here? For the shocker case, the shocker needed a special capability called capeduck read search. The read search allowed the container to enumerate the file descriptor, to change the inodes, and the duck, which stands for discretionary access control, allowed the container or Houdini within the container to read any file on the system while ignoring the discretionary access control on the file. So we could easily enumerate any file on the host file system. This is the capability required by Shocker. For our escape, we use two capabilities. One is capsys module, and this answers your question, which allows us to load new kernel modules into the kernel. And the other one is capsys log, which allows us to read information from the kernel. And I should say here that writing new kernel modules is very painful because you have to make sure that the version of the kernel module complies with the current kernel version, that the CRC and the max are equivalent to the current kernel modules. So there's a lot of stuff going on there. This is why we needed the capsys log to read some information and get the idea of what the kernel expects from our new kernel module. So capabilities were the trick here. And containers that are assigned capabilities are actually called privileged container. Now, I should say here that this is not something that we coined or invented. This is something that was known when Linux containers were developed and Docker containers were developed. But our contribution to it was to see how attackers, or in our case Houdini, might be able to leverage those capabilities to escape the containers. This was our contribution here, and we extended a bit the definition of privileged container, saying that a privileged container is a container providing an attacker with a direct or indirect access to the underlying hosts. This is what we've seen here, and capabilities are just one example of privileged, or just one example of how a container can be turned into a privileged container, but there are other ways to make a container or privileged container. And so today we talked about capabilities, but mounts can also make a container or privileged container. So for example, one of the most, I guess, weird or uncommon use cases is creating a container that mount the whole host file system. So you have a container that just owns the whole host file system. So this is obviously a privileged container. Another example of it would be no seccomp and no app armor. Now, Linux has a very effective and efficient security controls, seccomp and app armor, that implemented defense in depth in Linux. So those security controls allow us to restrict access to or access or execution of processes, even if those processes have certain capabilities. So even if our container have those capabilities that I mentioned before, with the right seccomp profile or app armor profile, the process and the container will be pretty restricted. So container without those security controls should be considered a privileged container. Last but not least, we have the Docker sock. I didn't cover it today, but I still thought it worth mentioning. Docker sock is a special file that allows the CLI, Docker CLI, to communicate with the Docker daemon. Now, any user or process that have access to the Docker sock file can control the Docker daemon. Docker daemon runs as root. So this is an obvious privilege escalation or escape, or in our case, when you talk about privileged container, if a container have access to the Docker sock on the host, it should be certainly considered a privileged container. So privileged containers were the trick. And what is the risk? I'll just recap. What is the risk of having privileged container within the environment? There are a couple of things to consider. For those of you who are computer science enthusiasts, I have here a reference to PNNP. I hope you'll appreciate it. So there's a couple of risks that we should consider. First is, of course, escaping. We just discussed this. Privileged containers can be used to escape. But of course, this doesn't stop here. As soon as our attacker or Houdini gets into the host system, any other container will be obviously compromised. Any sensitive data that are stored in there, credentials, and so on. There's another vector which leverages privileged containers to escalate privileges. So imagine this: you have a DevOps engineer in your company, in your organization, and he has access to a non-root access to a container host. Now, with his access, he does able to launch or deploy new privileged container. If he can do that, he could just launch a new privileged container, access it, and then escape it as root on the host. This is another vector or another risk we should consider when we have privileged containers or the permissions or the ability to launch new privileged containers. So this is the risks. What about mitigations? So there are a couple of things you should consider when thinking about privileged containers or the risk about privileged containers. First and foremost is the privileged access to the container host. Any user, any developer, any DevOps engineer with privileged access to a container host can inflate the attack surface of the environment dramatically by deploying privileged containers to their need. So controlling privileged access could be root or can be any user under the Docker group is critical to limit the ability or to limit the attack surface of the whole environment. This is the first thing to consider. Second thing to consider, we talked a lot about privileged containers and capabilities and so on. So limiting the ability to deploy a new privileged container is obviously a good way to limit the attack surface of the environment. So the CLI, the syntax that you see here, Docker run -- privilege, is one way to deploy a container with the whole 9 yards, the whole set of privileged containers, the whole set of capabilities, excuse me. I think there are 39 different capabilities at the moment, and this is still under development. And so Docker run dash privilege is one thing that you want to prevent when allowing user to run containers in your environment. And last but not least, we should also talk about secrets. Containers obviously are used in a multi-tenant platforms. It allows us the flexibility to run multiple sessions on the same host, which is great. The other side of it is that different session might be associated with different sensitive data, different set of secrets, different set of users. And so limiting the exposure of credentials in such environment is super critical, because if you have one privileged container within the environment and it is compromised, all the other containers will obviously be compromised, all the secrets and data and so on. This is why secrets, as in actually any other environment, the exposure of secrets should be minimized to the bare minimum. All right, so let's talk about key takeaways. Here's the thing. Although everything I said here today, containers can be a good security boundary with a little asterisk. We've seen that when we launch a raw Linux container, completely isolated, it will be very efficient in limiting the ability of the attacker to escape from the container to the host. But in many cases, operation or reality dictates differently and requires us to poke a new holes into the environment. And these holes inflate the risk that we need to deal with. So what kind of things we should consider? What risk you should consider if you have container environment within your organization? First one is privileged access to the host. This privileged access, as I mentioned before, will allow developers, DevOps engineers to launch privileged container and extend the attack surface. Privileged containers are obviously a risk and attack surface, and secrets that I just mentioned. This is the things I would recommend, and I know that many security, DevOps security vendors and service providers usually focus on the application layer, on the behavioral layer of the containers, but there are rare cases where I see, or I've seen in the wild, people that focus on the containers themselves and how they are configured and what permission or capabilities and what kind of boundaries or how the boundaries of the containers look like. So this is one thing to consider. And I didn't have much time to discuss all the details, so I'd like to suggest two things. First of all, you can have a look at our threat research blog, CyberArk Labs threat research blog, where you'll find the research that this session is based upon, with all the details that I mentioned before. This is the first thing. Second thing, I'd like to suggest that you come at our booth, at CyberArk booth right over here, where you'll find me. I'll either be there or in the Lego station trying to break the record there. That's it. Thank you very much. Any questions? Yeah.
So breakout relied on some fairly loose capabilities.
Are
there other breakouts that effective core capabilities are?
So, okay, so that's a good question. So the question was, here I showed escape based on capabilities. Are there any other ways to break out of containers? And the answer is yes. As I mentioned, containers that have pretty weird mounts. For example, there are several containers that are run as sidecars in Kubernetes environments that wrap or simplify the work with the Docker daemon. And to do that, those containers mount the Docker sock file that I mentioned. So this allows any user or process within this container to completely control the Docker environment. So this would be one thing to look for. there's other thing that I didn't mention here today, which is exploiting kernel vulnerabilities. Now, it's not a straightforward thing to do. Even pretty simple vulnerabilities or exploits like dirty cow can be exploited straightforward within the container. You have to adjust it. We have done some work around it, and you can find the piece in the threat research blog. But kernel exploit would be one way to go. Thank you very much, guys.